Welcome to this video on the topic of networks. In this video, we'll be having a look at something called a directed network. But before we go there, let's have a look back at some revision. When I say the word network, the first thing that probably pops into your mind is a diagram that looks something similar to this. So we've got a diagram composed of two discrete types of elements, that being nodes, as seen with the circles with the letters inside, and edges, those being the lines that link the nodes together. Now, this sort of network over here, we'd call this just a network, or if we want to be specific, we'd say it's an undirected network. The word undirected used because if we want to travel between nodes, we are able to travel in either direction shown on the edge here. So if we want to go from A across to B, we are able to do that. And similarly, if we want to go from B to A, we are also able to do that. There is no specification in the direction of flow along the edges. Now, this particular sort of figure we have over here, we call it a graph. Now, suppose we want to work on a network where traffic can only flow in a single direction. For example, if you're at node A, you are able to travel to B. However, it's a one-way trip. You are unable to go back to A. For that sort of network, we have something called a directed network. Now, the first thing you're going to notice in this figure seen over here is that it looks very similar to our undirected network. However, there are arrows on our lines or arrows on the relations that show how the nodes are connected to one another. Because there are arrows here, we call this a directed network. Now, a directed network itself, if we have a figure of a directed network, we no longer call it a graph, but rather we call it a digraph. Now, a directed network is composed of three discrete components. First one being the node, the second one being the edge, so everything that we've seen in this network over here, and then we've got something called an arc. Now, an arc itself is simply an edge that is only one-way traffic. So what we can see is that the relation linking D and B together, this is an arc. So you've got a line and it's got a single arrow on it. So you can go from D across to B. However, you cannot go in the reverse direction. You cannot go from B down to D in a single hop. Furthermore, we have this relation that links A and B together. So you've got two arrows on the line. This sort of relation over here, it's just another way of writing an edge to make it fit inside of a directed network. If you want, you can leave the arrowheads off. So in summary, for a directed network, we have nodes, we have edges, as we've seen before, and the new component we're looking at is an arc. Traffic may only flow in the arrow of direction. Alright, now that we've had a look at what a directed network is, let's have a look at how we can construct connectivity matrices from them. In example 1 over here, it says compute the first, the second, and the third order connectivity matrices. We have our digraph shown here, our directed network. What we want to do is we want to show how all of the nodes are linked together in our first order connectivity matrix. To do this, I'm going to follow the same process that we carried out in the previous lesson. That being is I'm going to count the nodes, and that is going to be the order of my connectivity matrix. So I'm going to go 1, 2, 3, 4, 5. So we need a 5 or a 5th order matrix to show our connectivity matrix. I've already gone ahead and I've pre-planned this on the page as seen. Now, next step is I'm going to label my rows and my columns. Now, as mentioned in the previous lessons, it's not necessary to actually label the rows and the columns. The reason I'm doing it is simply because it avoids me from making simple mistakes. What you're going to find is that questions in the future, the labels themselves aren't going to be on the matrix. Rather, the way in which you're going to know what row and what column corresponds to each node is you're going to have to look at the nodes you have and then do it in alphabetical order. Alright, next step is we have to look at the relationships between the nodes. So first node we're going to start at is node A over here. And we're going to observe what nodes we can travel to based upon the edges and the arcs we have available. Now, going straight from A to B, we can see that we're working with an edge still. So traffic is unidirectional. As a result, we are able to travel from A across to B. Consequently, the connectivity matrix to go from A to B, we're going to put a 1. Looking across, the other node that is connected to A is D. However, it's connected with an arc, and the arc depicts that the only traffic that can flow is in the direction of D to A. Therefore, if you are currently at A, you are unable to go to D in a single hop. Rather, the only place you can go to from A is simply B. Therefore, the row in this matrix is now complete. Moving across to node B. Node B, we have a number of options we can travel to. First one being is that we are permitted to travel from B to A across this edge. We are also able to travel from B down to C across this arc. And we are also able to travel from B down to E across this other arc. We are unable to travel to D because the direction of flow depicted by the arc connecting B and D together is from D to B only, not from B to D. Moving to our next node, we have node C. With node C, there is only one direction in which we can travel, and that is from C across to E. The connection between C and B is an arc, and the arc is stating that traffic may only flow from B to C. So we can't go from C up to B. Going across to D, following alphabetical order, we have a number of destinations we can get to. First one being is we can travel from D upwards to go to A. We may travel from D upwards to get to B. And we may travel from D across to get to E. And then we have our final node, node E. From node E, we are permitted to travel across to D and across to D only. Our options of travel on this one are quite limited. Reason being the relations linking E and B, D and C are arcs, and we are unable to travel in the opposite direction. And thus we have completed our connectivity matrix seen here. Now to finish this off, I will simply put in my zeros. Again, reason I'm writing them in red is purely for stylistic purposes because it makes it easier to see where you cannot travel and where you can travel. You're welcome to do your connectivity matrix all in one color. Now that we have our first order connectivity matrix as seen over here, we're able to generate our second and our third order connectivity matrices. Now to do that, all we need to do is create a new matrix, the same dimensions as our first connectivity matrix here. Now to generate the data that goes inside this matrix, we're simply going to use our calculators. Now as shown in the previous lesson, to generate the second order connectivity matrix, all we need to do is put in our first connectivity matrix, in which case I've already gone ahead of time and inputted the values. And then we simply need to square the first order connectivity matrix. What this yields is our second order. Understanding the results, if we bring up a new graph and we want to have a look at the locations in which we can get to, in our case looking at node A or starting from node A, first thing we're going to do is highlight A, and the rules in which this is going to work is that we're allowed to hop across our edges and arcs twice. So to go from this part here, we're going to hop once to B, then back to A. Looking at our travel from A to C, we're going to go once to B, down to C. And then finally, our travels to E, we go from A to B, down to E. So the principle of what we learnt in the previous lesson still holds, using it on directed networks as seen over here. Now, final thing to finish off this question is we're going to generate our third order matrix. Again, this is quite straightforward, as in we've already done the hard lifting. All we need to do is create another matrix of the same order as the previous two, and we're simply going to use our technology to fill in the information for us. So, bringing this up, I can simply scroll all the way back up again. We're no longer doing squared, we're going to do a third order, so I just cube it, and lo and behold, it reveals the answer to us, as simple as that. What you're going to notice about the data that you see over here is that as we're moving up the order of matrices or connectivity matrices, you're going to find that the numbers are increasing in magnitude. Reason for that is the more hops we enable ourselves to take, the more possibility of destinations we have to reach. So in our first order connectivity matrix, what you find is that there are only a small amount of destinations you can reach from a particular node. And similar for a second order, it doesn't really increase a whole lot. It does a bit, but not quite that much. But for a third order and up, the permutations of places you can get to increases at an exponential rate. So going from 3 hops, there are much more options you can take. Alright, now going down to the questions B, C, and D. State the amount of paths from D to A of exactly 2 hops. So what we're going to do to answer this question is we're going to look at our connectivity matrices, that being the one that shows 2 hops, in this case this matrix over here. Now it's saying the amount of paths starting from D and moving to A. So on the rows over here we have our starting location, and on the columns we have our destinations. So starting from D, A, B, C, D, so this row here, we're traveling to A, so we're going here. So of which there is one path, or there is one route we can take to get from D across to A. Using the subscripting, we could do it as C squared, and then it's going to be row. Alright, moving down, we have state the amount of paths from D to A of at most 2 hops. So we're allowed to use this second connectivity matrix, so second order, and we're able to use this first order. So the amount of hops is going to be, so D to A, it's going to be this element here again. So it will be C 4, 1 plus, and it's going to be C squared 4, 1. So we're going to be linking 1 and 1 together. Key wording is this was where it says at most. So you get to use the first order and the second order. So the result is going to be 1 plus 1, which will give us 2. Moving across for D, state the amount of paths from D to A of exactly, or state the amount of paths from D to A of up to 3 hops. So we're allowed to use 1 hop, 2 hop, and 3 hops combined together. So we're using this one here, and this one here. Consequently, we're able to say paths is equal to C41 plus C squared 41 plus third order. And I really shouldn't work across the page, but purely because I'm out of space, what we're going to do is go 1 plus 1 plus 2, and there are 4 paths. So easy as that. So in conclusion, what we had to look at in this particular lesson was we had to look at what is a directed network, what goes into making them, so the 3 explicit components, those being nodes, edges, and the arcs. And then we had to look at how we can generate connectivity matrices using our directed networks or our digraphs.